in the introduction, the expectation here is that you would have encountered a little bit of recursion as a programming technique in an introductory programming setting. And well, so lecture 4 is largely intended to be review. On the other hand, if you've never done that, if you've never studied recursion and you go through these notes and you pick it up and you feel comfortable with it, or you simply go back and repeat it a couple times, that might be okay too. But a critical point here is that I'm not expecting that you've done very much with recursion, but it is a fact that beginning in lecture 5, we're going to be putting recursion, recursive programming, to real purpose. We're going to get quite serious about using recursion as a programming technique henceforth. It's a very powerful technique, and like anything, it has its pluses and minuses, but the positive aspects of it in certain circumstances way outweigh the negative aspects. The negative aspects being some time delay sometimes. Okay, let's jump right into it. So, one thing I want to get out of the way, and this occurred to me in the prior lectures as well. In Java, the Java community speaks of methods, and if you've studied Java, if you've been learning to be a Java programmer, invariably you keep saying methods, methods, methods. C++ community tends to refer to functions instead, and there are yet other terminologies, and what I want to say loudly and clearly here is, in essence, all these things mean the same thing. Methods, functions, procedures, subroutines, it's all essentially the same game. You write a block of code, and then somewhere else in your program you invoke that code, you call it, you use it. The code that I'm going to present here in this section, basically I'll be speaking about functions. I'll be saying this is a function, etc., etc. But the code, while it's immediately C++ code, all you have to do to it to turn it into Java code is put the keyword static in front of it, and then you'll have what Java people call a static method. In other words, a method that does not act on objects. So once again, source code is available, as is true with all the code that I present. You can download executable code in C++ or Java. The expectation has to be that at this stage in the game, you've written enough code, either in Java or C++, to feel really pretty comfortable with this idea of a method or a function. Same thing, okay? But here I'm really thinking static methods again. We're not thinking object-oriented programming here, just methods that you can call from other methods. They don't act on objects, and so forth. Okay? And yeah, and you've been working with functions sufficient at this point that you realize that they provide a nice way to organize your code, make it more readable, more modular, makes it easier to maintain the code. Okay? But it's also, of course, really important to realize that what functions really do for you is they provide a way to write some code that does something, and then use that code, invoke that code from some other point in the program, and after that code finishes, it returns back to the point in the program where it was invoked. You know all this, but it's important that you really get your head around it. Okay, some functions are built into the language. I could name some things right here, but for example, square root. In Java, you have math.sqrt. That's the square root function. In C++, if you include the math library, you have a function called sqrt. Okay, but of course, real power of programs, functions, to a large extent, programmers write their own functions. Programmer decides that need a certain functionality, the ability to do something repeatedly, so the programmer writes a function, after which the program can use that function as many times, as often as they want, and anywhere in the program that they want. Okay, and here's a really important idea. So a function calls another function. It's possible that at this point you've only had functions inside main, or inside your main function you called other functions. Inside your main method you called other methods. But things are more general than that, of course. Inside any function you can call another function. Okay, inside any method you can call another method. And that function can call yet another function, and so forth. Eventually, all these functions return and you get back to where you started. Somewhere along the way, somebody got this idea in their head. They asked this question, well, what if a function could call itself? Would that be a useful thing to be able to do? And it didn't take long for people to appreciate that, yes, that would be a very powerful and a very useful thing to do. And that is what is essentially meant by recursion, or a recursive function. So now we have to remember a couple things before we hop into recursion. So functions have parameters generally. Okay, they don't have to have parameters, but in general, a function or a method has a parameter list. And as you know, these are special variables that are used to allow that function to receive information from wherever it's being called. Okay? So as we say, one function can pass information to another function by means of the second function's parameters. What you may not realize is that when that second function gets called, that's the moment when the parameters get created. Those variables don't even exist in memory until the function is called. Okay? We don't need to get into the nitty-gritty of how this all works, but suffice it to say that when a function is called, its parameters get created, and then when that function returns, those parameters disappear. And this is true when a function calls itself. And that's important. Let's imagine a situation now where we're dealing with a function f that has a parameter named n. It could be an integer parameter. It doesn't really matter. So you might think, okay, I look at the code and I see there's a function named f and there's a parameter named n. Clearly n is a variable, and you might think, well, there's just one variable named n. But here's what happens in the case of recursion. The function f will call the function f again. Somewhere inside the code for the function f, there's going to be a recursive call made to the function f. Okay? When this happens, this new call to the function f is going to result in a new variable n. At this point, you have two different parameters named n. One belongs to the original call to f, and the other one belongs to the new call to f. Okay? These are completely different variables that happen to have the same name. They occupy different memory locations. And this is really important in terms of the power of recursion. It's a very essential feature that makes recursion work. Here's a simple example. So, what does this function do? Okay, you pass it a number, an integer. It's received through the parameter n. Okay, then the value in n is checked. If it happens to be less than 1, this function returns 0. Otherwise, this function makes a recursive call to f, and it passes the value of n minus 1 to f. This is exactly where things can get confusing. What are we passing to f? We're passing the value that's stored in the original n minus 1, 1 less than the original n. But the critical thing to realize is that number, n minus 1, is going to become the value of the new parameter n for the new call f. That's what people have a hard time getting clear in their head when they're first learning recursion, seems to me. Okay, so that recursive call is made. Whatever that recursive call to f returns then gets added to the value of the original n, and the result of that addition gets returned by the function f. Yes, if you're not used to it, it's terribly confusing. That's why we're going to look at this thing in action. Okay, so here we go. Let's say somewhere in the code there's a statement that introduces a variable sum and sets it equal to f of 3. So the action really begins by calling the function f and passing it the number 3 as the value of its parameter n. Okay? Now checking the code for f, we notice that the value of n, 3, is not less than 1. Therefore, the function is going to execute this statement, return n plus f of n minus 1. And really, as I said, the action begins here by making the recursive call to f, and, well, what value are we passing to f? Okay, that's clear. The value we're passing to f is 2, because the value inside n is 3. So n minus 1 is 2. All right, we're calling f, passing the number 2, and that number 2 is going to become the value of the new n, of the parameter n for the new call to f. So here we go. There are now two different variables named n, one belonging to the original call, whose value is set to 3, and another n belonging to the new call to f, whose value is set to 2. Okay? All right. In a similar manner, that recursive call to f is going to wind up making another recursive call to f. And this third call to f will have its own parameter named n. So now there are going to be 3 different n's in this story. There are 3 different calls to f, and there are 3 different n's. and this third n is going to have value 1. Okay? That then is going to result in a fourth call to f. A fourth call to f, and its n is going to have value 0. Okay, so at this there are 4 active calls to f. None of those has returned anything yet. And so there are correspondingly 4 different parameters named n. The first n has got a value 3, the second n has a value 2, the third n has a value 1, and the fourth n has a value 0. Okay, well, in the case of the fourth call to f, since its n has value 0, and since 0 is less than 1, that f is ready to return its answer. It returns the answer 0. Okay, but where does it return it to? Okay, it returns it to the point in the third call of f where the third call made the fourth call. It's basically like this. Back there in the third call of f, which has a parameter n whose value is 1, we're now ready to compute 1 plus f of 0. Okay? F of 0 is 0. That was the answer returned by the fourth call of f. Okay, so that 0 gets added to 1, which is the value of n, and we now have the answer to the third call's computation. The third call of f is now ready to return the number 1 as its answer. And it, of course, returns that back to the second call of f. Aha, so the second call has an n whose value is 2. And the code basically comes down to computing 2 plus f of 1. Well, we just got the answer for f of 1. f1 is equal to 1. So the computation 2 plus 1 is made, resulting in 3. And that is the answer to the second call's. That's the value that the second call is now going to return. The second call is going to return the answer 3 back to the first call. And, of course, back there in the world according to the first call, there's an n whose value is 3. And that gets added to the value that was just returned by the second call. So that results in 3 plus 3, which is 6. And that, at last, is the answer that the first call of f is going to return back to the original call to f. There was the original call to f which said int sum equals f of 3. Okay? We now have the answer to f of 3. f of 3 is equal to 6. So this statement right here, the upshot of it is just going to compute the number 6, and the number 6 is going to get stored in sum. Okay? Now this next bullet says be sure that you follow the details of this example. Well, I mean that, but I understand that it is tricky. If you're not well versed in recursion already, this may still seem a bit murky to you. I'm hoping that this next figure will help you to come to terms with this better. Okay? So here's the game we basically played. We originally were asked to, the code was originally asked to compute f of 3. So this resulted in a call to the function f, and for that call to f, there's a parameter whose value n is equal to 3. But of course that resulted in the need to call f again and pass it the value 2. The value 2 became the value of the second call to f's parameter n. That then in turn resulted in the need to compute f of 1, resulting in a third call to f. Okay? that call to f has its own parameter n, which is set to 1. Okay? And again, there's a call to f passing it the number 0. The number 0 becomes the value of its n. All right, and that's the end of the recursive calls. That fourth call to f quickly returns its answer 0 back to the third call. Okay? Which takes that answer, adds its value of n to it. 1 plus 0 is 1. And it returns that number 1 back to the second call. Okay, the second call takes that number 1, adds its value of n to that, resulting in 3. And again, that 3 is the answer returned from the second call back to the first call, where that first call takes that 3 and adds that 3 and the value of its own n, which is also 3, and it comes up with the answer 6, and it's the answer 6 that's returned, and we can basically say that f of 3 is equal to 6. Okay? And so that's why the number 6 got stored in the variable sum. What we're saying here about each call of f having its own parameters, this also applies to any local variables that the function f has. Anytime you call a function, if that function has local variables, then those local variables are created at the time when the function is executing, and when the function is done, they disappear. So as I said, you probably, hopefully, came into this course having been exposed to recursion already, in which case what we've done so far is maybe just a review, pretty much. But thus far, including what you've looked at in this lecture so far, you probably haven't been exposed to really practical usage of recursion. Tends to be when you're introduced to recursion, you start with some examples that, while they are useful in getting the idea of recursion across, they aren't particularly useful. Okay? Beginning in the next lecture, we're going to actually do some very useful things with recursion. Let's look at one of the classic examples used to introduce recursion, and it really shows off recursion in a poor light, in a sense, because it's actually quite a wasteful, very inefficient way to compute something. But there's no doubt that it does very much highlight how recursion works. Okay, and so that's the standard classic example of using recursion to compute Fibonacci numbers. Fibonacci numbers, as explained a little later in a couple slides, but I'll take care of it now a little bit. If you don't know the Fibonacci numbers, they're a sequence of numbers that have the property that each number is equal to the sum of the two that immediately precede it. Okay, we'll see this in detail in a little bit. Let's look at this recursive code for computing Fibonacci numbers. Okay, besides the parameter n, I've also got a couple local variables a and b. Strictly speaking, I don't need them. I could have coded a different way and avoided them, but I wanted to show off a couple local variables here. So let's take a look at what this does. Similar to our previous example, if n is less than 1, then this function just quickly returns the answer 0. Done in that case. Otherwise, and by the way, you might feel the need to stick an else in here. You could put an else in here optionally if you want to. it actually makes no difference whatsoever, because if you think about it, if n is less than 1, it's going to return 0, and that's the end of it. Otherwise, it's going to continue to the next line. Okay, so this next line says, if n is equal to 1, return the answer 1. All right, well that covers the base cases, the non-recursive cases. If n is bigger than 1, though, we fall down into the remaining code, which clearly makes recursive calls. And not just one recursive call, but actually makes 2 recursive calls. It calls Phoebo and passes it 2 less than the value of n, and then it calls Phoebo again and passes it 1 less than the value of n. It records the answers from those 2 recursive calls in the local variables a and b. It adds those together and returns the answer as its return value. Okay, so Phoebo of 0 is clearly 0. Phoebo of 1 is clearly 1. All right, what about Phoebo of 2? Well, Phoebo of 2 is going to call recursively calling of 0 and Phoebo of 1 and adding them together. All right, so we see that that's going to be 0 plus 1, and that is equal to 1. Okay? How about Phoebo of 3? Well, similarly, Phoebo of 3 is going to require recursive calls to compute Phoebo of 1 and Phoebo of 2 and add those answers together. And so what did we say? Phoebo of 1 is 1. Phoebo of 2 is also 1. So 1 plus 1 is 2. So Phoebo of 3 is going to be 2. Okay? Phoebo of 4 is going to be the result you get from Phoebo of 2 plus Phoebo of 3. So that's going to be 1 plus 2 is equal to 3. Phoebo of 5 is Phoebo of 3 plus Phoebo of 4, which is going to be 2 plus 3 is 5. Okay? Continuing one more time, Phoebo of 6 is going to be Phoebo of 4 plus Phoebo of 5, so that's going to be 3 plus 5, that's 8. And so forth. Okay? It does indeed generate the sequence known as the sequence of Fibonacci numbers. Here we're seeing the numbers that we just considered, right? So Phoebo of 6 is 8, which is 3 plus 5. 8 is 3 plus 5. This is a horribly wasteful, highly inefficient way to compute the Fibonacci numbers. Let's think about it. When we're computing Phoebo of 5, Phoebo of 5 makes recursive calls to compute Phoebo of 3 and Phoebo of 4. All right? But Phoebo of 4 also makes recursive calls. It makes a recursive call in particular to compute Phoebo of 3. So you've got Phoebo of 5 using Phoebo of 3, and you also have Phoebo of 5 making a separate call to Phoebo of 3. So basically, when you compute Phoebo of 5, there are going to be 2 recursive calls involved for the purpose of computing Phoebo of 3. Okay, there's redundant work done there. But it gets even worse if you think about how many times Phoebo of 2 is computed from scratch. In calling Phoebo of 5, turns out Phoebo of 2 will be computed from scratch 3 different times. So I'm going to close these notes by showing you, this lecture is going to close with a non-recursive function, and I don't want to spend too much time on this function because it is not recursive. It doesn't show off what it is that I want you to really learn, and I don't hold you responsible for this particular code. But I think it's important to be honest about things. The examples of recursion that we've seen so far are not very efficient, and they don't really have much compelling about them. And in fact, the FIBO function is a terrible function. It's incredibly wasteful. And here's a different function that is non-recursive. It uses a loop instead of recursion, and it computes its Fibonacci numbers just fine without all the wasteful repetitive work. Okay, I don't want to spend too much time on this, but basically A, B, and C throughout the loop are going to be 3 consecutive Fibonacci numbers, and as you go through the loop, you advance those 3 Fibonacci numbers. Okay, if you're interested, you can take a look at it, but as I say, you're not really responsible. So it seems that with this, I'm pretty much saying recursive programming, recursive functions are terrible. They're a waste. Okay. So anyway, I'm definitely not saying that. And the last thing I want to do is leave you with the impression in this lecture that recursive programming is a bad thing. It's not. It's a very useful thing, and it simplifies a lot of programming. If there's an efficiency penalty for using it, it's actually, in practical cases, it's actually a minimal one, and nothing at all like the FIBO example just looked at. So keep an open mind about recursion. It's important. When we get to the next lecture and learn about merge sort, and then the other sorting method, the last of the 5 basic sorting methods that I want to cover early, called quicksort, that's another example where recursion is going to prove to be very useful in thinking about and coding the algorithm. Okay, so as usual, take the self-quiz when you're ready, and good luck.